Okay, so I'm going to go over the exam solutions quick, and I'm going to try to show kind of a couple different approaches to doing each one of these problems. So I'm going to go through this fairly quickly because I don't want you guys to have to watch this for a long time. So exam 3 solutions. All right, and I don't have a printed copy here, so I got to toggle back and forth between my the electronic copy and my solution set here. All right, the first one is the eccentricity. Let me get this in full screen. Yeah, the eccentricity of a frozen pizza. Well, we know that, hopefully we know, and for those who didn't know, a frozen pizza is a circle. And so we know by definition there that E equals C over A, which in this case equals 0. The other way to think about that is that if you don't remember this, the equation of a circle is like x squared plus y squared equals r squared. Well, if you think about, well, eccentricity, really you think of an ellipse, so you could write this as x squared over r squared plus y squared over r squared equals 1. And this is really a squared and b squared. And we know for an ellipse that c squared equals a squared minus b squared, which equals 0, which means the eccentricity is going to be 0. All right, so that's for one part A. And part B, I think, was the I cross J stuff. Yeah. So by definition, I cross J, what is that? That just equals K hat. Okay. If you weren't sure about that, you could do it this way, where you have I, J, K, and then I. This is supposed to be a cross. I is 1, 0, 0, and then J is 0, 1, 1. And you take the determinant of this. Well, the only one that isn't going to go away is the K, because all the rest have zeros in them. And so it'll be 1 minus 0 K. So that just becomes equals K. And then I dot J, right? How does that work? Well, remember that the equals the magnitude of I times the magnitude of J times the cosine of the angle between them. Well, the cosine of the angle between them, oh no, cross J, sorry. Oh no, we did this one, yeah. And then the angle between them is 90 degrees. They're orthogonal, right? So the cosine is 0. So this becomes 0 that way. The other way to do that would be to say 1, 0, 0 dotted with 0, 1, 0, which equals 1 times 0, and 0 times 1, and 0 times 0. So either way, that equals 0 as well. Okay, the next one is J cross I, and we know that J cross I will equal the opposite of I cross J, so that equals negative K. Or likewise, we could use the determinant method, I, J, K, and this will be J cross I, so 0, 1, 0, and 1, 0, 0. Again, K is the only one that doesn't disappear. So that would be 0 minus 1 K, so that equals minus K. All right, and that's the next one. Given the points 1, 2, 3, and 6, 5, 4, find the vectors P, Q, and QP. So, so this is number part C here. P is 1, 2, 3, and Q is 6, 5, 4. And so PQ is just the vector that goes from this one to this one. So that becomes 5. To get from 1 to 6 is 5, 6 minus 1. To get from 2 to 5 is 3, and to get from 3 to 4 is 1, like that. And QP, well, that just is the opposite of this. To get from 6 to 1 is negative 5, so you could write that as negative 5i. And then to get from 5 to 2 is, or from 2 to 5, 5 to 2 is negative 3. J, and then to get from 4 to 3 is a negative 1. K. Right, so either form is acceptable here to get this. Now to get P cross Q, or to get PQ cross QP, which I think is the last thing we had to do here. Yeah, PQ cross QP. Where did my thing go? There we go. PQ cross QP. Well, what is that? The definition is the magnitude of PQ times the magnitude of QP times the sine of the angle between them. And all that, so this will give me a big scalar, times the unit vector normal to both of them. Well, right away I know that the sine of the angle between them, since these are just opposites, they're two vectors pointing in opposite directions, the sine of the angle between them is 180. The sine of 180 is 0, so that equals 0. Alternatively, you can do it the determinant method, which we could do as this. I think I've got room. I, J, K, and then that's PQ cross QP is 5, 3, 1, and then negative 5, negative 3, negative 1. So if you notice that it'll always be, this minus this, which would give you negative 15 minus negative 15, so that's 0, and then this minus this, so it's 0, and so that works out to be the vector 0 there too. So that's, and if you just put scalar 0 as I did here, I'll accept that, but really, to be technical, you should call it a vector 0. So then D, the parametric equation for the line that is parallel to the vector 2i plus 4j, 2 plus 4 minus 6. So let's go to the next page. So 2i plus 4j minus 6k, and then the point is 357. And there's a number of ways to do this, and this is part D. But I think the easiest way is to say x equals, well, I'll start my original value, plus 2t. Y equals my original value, 5, plus 4t. And z equals 7 minus 6t. Okay, and of course you could have anytime you use this point, I could make this 4, 8 minus 12, or I could make this some other point on this line if you want to be just difficult. But for instance, I could go I could make all these negative, and that would work. But hopefully most of you got this. I haven't looked at the exams yet, so I don't know how things are going to shake out. All right, what's next? Find the equation of the plane normal to vector PQ from above and containing the point P from above. So vector PQ was, I'm going to do this over here. This is number 2. PQ, if I recall, was 5, 3, 1. And the point P, I believe, was 1, 2, 3. So 1, 2, 3, yeah. P is the point 1, 2, 3. Okay. One way to do that is to say, you remember the equation of the normal vector, which PQ is just the ABC. So I could say that this is 5x plus 3y plus z equals, and then it's the ABC times my known values here, so it's 5 times 1 plus 3 times 2 plus 1 times 3. So it's 5 plus 6 plus 3 equals 14. The other way to do that, if you didn't remember this kind of definition, you could do it by saying, well, I've got some vector PQ, and I've got some, some other random, I've got a point here, which I know is 1, 2, 3. And I've got some other point over here, which is x naught, y naught, z naught. Oh, no, sorry, I'm just going to call it x, y, z because that will save me a lot of ink. So I've got some point here, which is x, y, z, right? And I could draw another vector like that. Well, if this vector here is a vector in the plane, and this is PQ, this is the normal vector, then I know that these have to be perpendicular to each other. Which means if they're perpendicular, what does that mean about the dot product? The dot product is 0. So I could say that this vector, which is 5, 3, 1, dotted with my vector, this vector here, which is x minus 1, y minus 2, z minus 3, well, that has to equal 0. So this will be 5x minus 5 plus 3y minus 6 plus 1 times this is 1z minus 3, so z minus 3, and that has to equal 0. Well, I can move these to the other side, so I add plus a 5, plus a 6, and plus a 3, and that gives me 5x plus 3y plus z equals 14. Okay, so 2 ways to do that one as well. All right, now number 3. This is the one that I think a lot of people got hung up on. So let's take a look here. We'll zoom in a little bit so you guys can see better. Zoom, 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 zoom. Why didn't that work? Well, hopefully you guys can read this. No, but you know what I'm going to do is pause for a second, open this in a different program so I can zoom in. Okay, so here we are again. The first part, 3 points, find the normal vector to each plane. We're trying to find this line of intersection, L, between the two planes, because where two planes intersect, well, that gives us a line. And so hopefully you guys either had on your sheet, or you remember, or we've done this several times before. The normal vector of the plane is just this. So the first normal vector, so we could call it n sub m, would be 1, 2, 3. And the other normal vector would be 3, 2, 1. So I tried to pick nice easy numbers there. So part A, so this is number 3, part A, so the normal vector m would be just simply 1, 2, 3. And then the normal vector of the other one, the normal vector to the n plane would be 3, 2, 1. Okay. So what's next? I gotta keep toggling the right thing. So this is a parallel or orthogonal question. Any line on a plane is parallel or orthogonal to the normal vector of that plane. Well, we should remember that a line in the plane has got to be orthogonal to, so it's got to be orthogonal to the normal vector in the plane. So part B, we know it's orthogonal. Now, why did I ask that question? Because, so if we know that any line in a plane, so the line of intersection, right, true or false, the line of L lies in both planes M and N, right? So if this line of intersection has got to be in both planes, and I know that any line in a plane is orthogonal to the normal vector, then the line L, the line of intersection, has got to be orthogonal to both of these vectors, right? So how can I explain this otherwise? My line L has got to be orthogonal to this vector, and it's got to be orthogonal to this vector. So if I just simply want to find a vector that's parallel to that, well, I can just take the cross product. C is true or false. Line L lies in both planes. Okay, that's true. What the heck is going on here? Okay, so C is true, and D is find the vector parallel to line L. Well, the vector parallel to both of these normals is the cross product. So that goes I, J, K, 1, 2, 3, and 3, 2, 1, and that equals 1 times 2 is 2, minus 6 is negative 4i, minus, okay, so I cross out the j, 1 times 1 is 1, 3 times 3 is 9, so that's 1 minus 9 is negative 8, so that's plus 8j, and k, cross that out, so that's 1 times 2 is 2, minus 6 would be minus 4. Minus 4k. So that would be a vector that's orthogonal to both of the normal vectors, so it must be parallel to the line of intersection between the two. Next up, E is what is the z coordinate? Now I'm kind of going on a different tack here, but hopefully you guys just can roll with me. What is the z coordinate in the xy plane? Well, that's kind of a dumb question. In the xy plane, if I'm on the xy plane, the z has got to be 0, right? So the answer to that one is the z coordinate in the xy plane is 0. Right? Why did I ask that? Does the plane M ever intersect the xy plane? Well, M is tilted somehow, right? So it must cross the xy plane at some point. So yeah, I mean, it's got to cross. So F is yes. G is yes. So F, yes. G, yes, because both of these are tilted. Now, at this point, you might think, you don't have to, but you might think, what happens when a plane intersects a plane? So when my plane M intersects, well, that's going to make some line. When my plane N intersects the xy plane, that's going to make some line too. So that's interesting, right? But big deal. But then I say, determine the equation of the line of intersection between planes M and N. All right, well, the way you should go about this is that, well, to get a line, and this is E, F, G, H, to get a line, I need a point and a vector. Right? Well, I've already got my vector, right? That's this vector that's orthogonal to both. So I can check that off as check. But I still need to get this point here, don't I? But I realize, wait a minute. If both these planes cross the xy plane, if this plane intersects the xy plane, well, the z coordinate there must be 0. Same deal with this other plane. Where it intersects the xy plane, the z coordinate must be 0. So my two planes were 1, 2, 3 equals 6, and 3, 2, 1 equals 4. And if z is 0, so when z equals 0, M becomes 1x plus 2y plus 0 z, or shoot, that's not right. Z is 0, so that should be plus 3 times 0 has got to equal 6. And so that also means that 3x plus 2y plus 1 times 0 must equal 4. Well, here, what do I have? I have the equation of two lines. And these are the lines where this plane intersects the xy plane and this plane intersects the xy plane. So if I can find the intersection of these two lines, well, then I'm in great shape. So where I left off here, so this thing came from plane M, and this one came from plane N, and I knew that when they intersect the xy plane, I get z is equal to 0. So I can take these two equations and solve them simultaneously. I'll subtract this one from this one. So I get negative 2x equals, well, that goes away, and then that's 0, and 6 minus 4 is 2, which leads me to that x equals negative 1. Sorry, I'm trying to concentrate here and while he's crying. Okay, so this is negative 1 plus 2y equals 6. So 2y equals 7, so that means y equals 3.5. 3.5. Let me just check it here. 3 times negative was negative 3. Plus 2y equals, so I add the 3, so that's 7, so y equals 3.5. So this is a pretty important step here. And I got to pause again and go check on Wally. Alright, well, you may notice that there's some rock and roll Christmas tunes going on in the background, and that seems to be the only way I can appease little Walter right now. So he's listening to me do calculus. You have to listen to us listen to music. So anyway, now we've got these 2 points. X equals negative 1, y equals 3.5. What are those? This line is the intersection of this plane and the xy plane. This line is the intersection of this plane and the xy plane. And so where 3 planes intersect must be this. So we've got a point x equals negative 1. Why am I doing it this way? Y equals 3.5 and z equals 0. Now this is one of many, many points, an infinite number of points on the line, but this is just one that's convenient for us to find, right? And way back when we looked at this problem back here, where we had a point. No. Where is it? Yeah, this point where we had this point and then this vector. So same deal. Now we've got a point and a vector, and here's our point. Our orthogonal vector is here. This one must be parallel, so we can say finally that our point, or the parameterized line, is x equals negative 1 minus 4t, y equals, let's see, 3.5 plus 8t, and z equals where is it? Where are we? 0 minus 4k, so minus 4t, which makes sense because our original point is right on the xy plane, where z equals 0. So this is the final answer. Surely you guys all found that to be the hardest problem. I tried to step you through it as much as possible, but there it is. Okay. Next up. And what was the next problem? We've got to go down here. In this problem, you'll find the area of overlap between 2 circles. All right. So first we have to sketch the 2 circles. X minus 2 squared plus y squared equals 4, and x squared plus y minus 2 squared equals 4. So these are 2 circles of the same radius. This is number 4. Switch back to black here. We notice that the radius is 2. And one is shifted 2 to the right, and we can say that looks like that. And the other is shifted 2 up, so we can say that looks like that. And so these are our two lines. So this is let's see, this is shifted to the right, so this is x minus 2 squared plus y squared equals 4. The center, of course, being at 2. And this one up here is x squared plus y minus 2 squared equals 4. And the circle here is, the center is at 2. But we also know that, you know, you could figure this out, that when theta equals 0, the cosine equals 1. So then it would be, we know it's 2a times something. So this one becomes, let's do this in a different color. This is r equals 2a cosine theta, and this one over here becomes r equals 2a sine of theta. Now the next part of the question, let's check that. So here we sketch the two circles. We know that the one on the x-axis is cosine, the one on the y-axis is sine. We label each circle. The next part is what is the appropriate value of a to make the Cartesian equations match the polar equations. All right, so we got to figure out what a is. Well, when cosine is 0, cosine of theta is 1. So a really becomes the radius, right? Because I've got to go all the way out to 4 right here. So at theta equals 0, we have to be at 4. So that means a equals 2. Okay, and then, you know, kind of by the symmetry up here, a equals 2 there as well. And what is the next part is find the area of overlap between the two circles. And you may leave your answer in integral form, all right, because I didn't want to spend a bunch of time going through this integral. So really, what are we after? We're after, you know, this area in here. So one way to do it is to integrate, you know, this circle. So we could integrate from, well, let's look at it this way. If I do this in green, I know that this line here, the line of symmetry between these, just by symmetry, we can tell this is theta equals pi over 4 here. Now, I want to make this as easy as possible. So I could integrate this circle from, well, I'm trying to get all this area, so I've got kind of different bounds at different places, right? So here my radius really is kind of this radius minus this radius. You know, I'm gonna draw a zoomed in version of this here. So let me go back to black. I'm gonna draw this really nice and big. And so we've got this kind of football-shaped thing that goes like this, and then we've got on the other side a circle that goes like this. And I've got my green line of symmetry in here. Now I want to make this as easy as possible. I could integrate here. But the problem is, you know, at some point my triangle goes from, so this is kind of my typical triangle, so I'd have to integrate from here to here. Or I could integrate this circle, and my typical triangle would go, you know, kind of my differential element would go like this. But at this point it changes. Right, so here I'm working on the sine circle, here I'm working on the cosine circle. So I've got really two options. My two options being, one is the integral from 0 all the way up to pi over 4 of, for, this is the sine circle, the upper one, for sine theta d theta, right? from 0 to pi over 4. And then the other, and so that gets me to kind of the lower half. Let's do that. Well, I'm not being very smart about my color coding here, but let's do that in black. Or I could do it in red to get this part here. That would be the integral from pi over 4 to pi over 2 of, let's see, this is the circle that is on the x-axis, so that's 4 cosine theta d theta. And you could just add these two, or you could say it's 2 times this one or 2 times this one. So we could add this. Or another acceptable solution would be, let me get rid of this. So add these two. Or multiply one of them by, hello, where'd you go? By 2. All right. So that's number 4. I was hoping that one was doable. You guys all asked very good questions in class about these areas in polar coordinates, and I said you could leave them in integral form, but even it wouldn't even been that tough of an integral to do. So here we are. Next is number 5, and what was number 5 about again? Oh yeah, this guy here. I was hoping this one would be kind of a layup for you, but maybe it was so long ago that we forgot. Conic section has the following properties: symmetric about both x and y axes, which is nice, so that means it's kind of centered at 0, 0. Crosses the y-axis at y equals plus or minus 3. We don't know much about the x-axis, just the y-axis, but it has foci at 0, plus or minus 5. So let's draw a quick sketch of that and see what we can get from it. And this is number 5. Do this on a new page. Number 5. So we've got this thing here and this thing here, and we know it crosses at 3. So I've got some intercepts there and intercepts there. But I also have foci at up here. There's a focus up here. And I've got, go 2 more units down this way, and I've got a focus down here. Right? And so if my foci are outside my vertices, that means that C is greater than A, which means that it must be a hyperbola. Or it has to bend this way. It always bends towards the focus. And so that means it's got to bend away from each other. So we know that this thing looks like this. You know, I don't know exactly what, but I know it's a hyperbola at this point because it always bends from the vertex towards the focus. Like this. All right. So I know that it opens up and down, so I know it's y squared over something minus x squared over something equals 1, right? It opens up and down, and the vertices are at 3, so I know this is 9. I know the foci are at 5, and so I know that c squared equals, for a hyperbola, it's, as one student pointed out, it's the opposite of this, so c squared equals a squared plus b squared, and so I know this, the foci are here at 25. 25 equals 9 plus b squared, so that means b squared must be 16. So that's like that. And so the last kind of important thing would be the asymptotes for this guy. So asymptotes would be, we know it's y equals plus or minus, you know, the thing that's under y over the thing that's under x, so that's 3/4. So the slope is a little bit less than 1. So the asymptotes are going to look something like this. And that's about all there's interesting there is to write about this one. And pretty much if you get any of this, you know, if you get the sketch right and the asymptotes right, you'll get full credit for that. Let's see what else. That's about it. Sketch a graph where appropriate, axes, vertices, directrices, etc. So I'm going to be pretty liberal with that because I just wanted to get the asymptotes because that really helps you draw it. Okay, that's the solutions. I hope you enjoy your weekend, and good luck on all the other finals. If you have any questions, please feel free to email me. For those who are moving on to bigger and better places, good luck. To those who will be back in the spring semester, I look forward to seeing you in the hallways. Take care.